Hi, everyone. Hope everyone is doing okay. Under the topic calculus, we need to understand the relationship between a cubic graph and its derivatives. Now, when given a cubic equation, for an example, x cubed minus 6x squared plus 9x minus 4, it is important to understand that when you derive for the first time, the first derivative of the cubic graph is actually a quadratic function. So if you were to derive x cubed minus 6x squared plus 9x minus 4, you'll end up with this quadratic function. So the first derivative of a cubic graph is a quadratic. X cubed derived became 3x squared, negative 6x squared derived became negative 12x plus 9x derived became plus 9 minus 4 will give you 0. So the first derivative of a cubic graph is a quadratic function. You can derive further the second time, and when you derive for the second time, you form a straight line function. So if you look at this again, you will be able to see that in the first derivative, it was quadratic. When you derive for the second time, you eventually form a straight line equation. So it's important then to know the relationship. How is the cubic related to its first derivative, and how is the first derivative related to its second derivative? So goes the story. Let's begin with the cubic and the first derivative. Now, when given a cubic equation or a cubic graph, like the one that we're looking at right here, that is my cubic graph. You can see from here on that there are turning points at this position, and there's also another turning point at this position. We did say to ourselves earlier that when you derive a cubic, you're going to form a quadratic, or the other name is a parabola. So here is the relationship. The x coordinates of the turning points of the cubic, the x coordinates of the turning points of the cubic graph are actually the x-intercepts of the quadratic or the parabola. Let me say that again. The x coordinates of the turning points of the cubic in the parabola, in the first derivative, they serve as the x-intercepts. And that's my point here. The x-coordinates of the turning points for a cubic graph, f of x, are the x-intercepts for the quadratic graph. That is super important. But there's more. Now, I need you to understand that the point of inflection, and the point of inflection is usually between the x-coordinates of the turning points. Actually, when you want to find the point of inflection, one of the ways to do it is to add the x-coordinates of the turning points and divide by 2. This x-coordinate of the point of inflection is actually the x value of the turning point of the parabola. So if you have your x-coordinate of the point of inflection somewhere here, then that x value is actually your x-coordinate of the turning point of the parabola. So let me get this clear. In the x-coordinate of the turning point of the parabola, we also know that it is supposed to be the axis of symmetry. So if I was to put this properly, I would say the x-coordinate of the point of inflection in the cubic graph is the axis of symmetry for the parabola, and further on, it is the x-coordinate of the turning point of the parabola. This is my statement right here. The x-coordinates of the point of inflection in a cubic graph is the x value of the axis of symmetry in our quadratic or our first derivative. Now, let's go. If you look at your cubic again, remember we're comparing the cubic and its first derivative. If you look at your cubic, now this portion of the graph, the gradient is actually increasing. It's positive gradient. It's greater than 0. Now, this portion where the gradient is greater than 0 will correspond to the part of the quadratic where the graph is above the x-axis. So whenever you look at the gradient of the cubic, and gradient is derivative of f of x, whenever it's greater than 0, which means it is positive, then in the first derivative, it's going to be the part of the graph where it is above the x-axis. Similarly, if you were to look at the portions where it is negative, that means the gradient is going downhill, or rather, the graph is going downhill and is negative. It corresponds to the portion of the quadratic where it is below the x-axis, just like what you're seeing there. Again, you continue. The gradient is now positive. The graph is increasing. The graph of the cubic is increasing. The gradient is positive. So in this case, it will be above the x-axis. So that's how it corresponds in this instance. And I put this across here to say, when the cubic graph of f of x is strictly increasing, that means I'm dealing with the gradient. The derivative is greater than 0. It means we're looking at the parts of the graph of the quadratic where it's above the x-axis. When it is less than 0, when it is decreasing, then it is below the x-axis. So let's summarize this part. We say to ourselves, the x-coordinates of the turning points, what are they in the quadratic? They are the x-intercept. We say to ourselves, the x-coordinate of the point of inflection in the cubic is the x-coordinate of the turning point in the quadratic. It is the axis of symmetry. We say to ourselves, when the gradient is positive, that means the graph of f of x is strictly increasing, then it means the graph of the quadratic is above the x-axis. And then when it's now decreasing, the cubic is below the x-axis, increasing, it is above. That's the relationship between a cubic graph and its first derivative. Let's go further and get down to an example. So if you see in this example here, look at it. You've got the equation of the cubic, which is the blue graph, and then the first derivative being the quadratic right there. Now, in the blue graph, the cubic, the x-coordinate of the turning point is at -2. The other one is at +2. Then I notice that the x-coordinates of the x-intercepts are actually at -2 and +2 for the first derivative. So for the first derivative, x squared minus 4, our x-coordinates of the x-intercepts are actually the x-coordinates of the turning points of the cubic graph. And then further on, like I had said, you can find the x-coordinate of the point of inflection of the cubic, which will be -2 plus 2 divided by 2. Remember, I said you can add the two x-coordinates of the turning points, and then you can divide them by 2 to get the x-coordinate of the point of inflection. That x-coordinate of the point of inflection in the cubic will be at 0 in this particular case. And what is it in the quadratic? It is definitely my x-coordinate of the turning point, which is occurring when x is 0 and y is -4, but also it is the axis of symmetry. Very important to understand that concept. All right, perfect. Let's break it down and go to the other part. Now, when you have dealt with the cubic and the quadratic, let's try and deal with the quadratic and the straight line, the second derivative and the first derivative. Now, notice, in the quadratic graph, the x-coordinate of its turning point in the quadratic, in the first derivative, is going to be the x-coordinate of the x-intercept of the straight line. So the x-coordinate of the quadratic is the x-intercept of the straight line. Again, similarly, when the graph of the quadratic is going down or decreasing, then we are looking at portions of the graph of its second derivative, which will be below the x-axis. And similarly, when it is increasing, when the gradient or when the graph of the quadratic is going up in the straight line, the second derivative, we're looking at portions of the graph where it is above the x-axis, when the second derivative when it's below the x-axis right there. So that's exactly what you are looking at. So remember these very important relationships. Just to probably summarize it nicely, I did put a graph here with its cubic, with its straight line, and with its quadratic as well. Then the summary would look something to this effect. When you're dealing with the cubic graph right there, we say your turning points of the cubic graph in the quadratic, they are x-intercepts. Still, when you're dealing with the cubic, the x-coordinate of the point of inflection in the cubic will be the x-coordinate of the turning point in the quadratic. Further on, it becomes the x-intercept of the linear graph or the straight line function. So basically, those are the relationships. In my next video, I'll be showing you guys what to do when faced with questions that ask about these particular relationships. Keep checking and keep liking the videos. Thank you so much. I'll see you soon.